started now. Thank you so much for coming, for attending the CSP seminar talk for this week, and we also have some like attending on the room. So just to give a brief introduction before you get started with this very interesting, exciting talk, I'm really look forward to that. So a very honored to invite Professor Javi Zhou, who is currently an associate professor in the School of Information at the University of Michigan. And before joining us here, so Professor Zhou was a professor of computer science at the Michigan State University. So he got his PhD degree from the Arizona State Universities in the 2014. And his research is broadly in the large-scale machine learning and the data mining, especially for the biomedical informatics. So I'm really excited and look forward to learn from like his talk today. So he also served as the program committee for quite a few like top avenue conferences, including the NeurIPS SML. And Professor Jia Zhou also got a lot of like funding support from the NSF, NIH, the LNR, and he also have a very long list of the awards, including many best paper awards, and also the career awards from the NSF, and also the best student paper from the International Conference of the Data Mining, and also the best student paper award in the International Symposium on the Biomedical Imaging, and a lot of things. So to avoid like the further ado, I will just give a chance for Professor Zhou to share with us his very exciting research work. Thank you.
Thank you, Lyra, for thank you for inviting, and then it is very nice to be here, share some of the work we have been done for the past I would say 5 to 10 years, on the dementia care. So yeah, so I don't know like how many of you know this, but this is one of the early human civilization writing where we start to put the knowledge, curate it together, and then trying to put it on the wall so we can record it, we can persist it. That is like 5,000 years ago, all right? And then knowledge is so important in this human civilization, right? So I like this, like the knowledge is power, right? So if we translate to English, and then it's and talking about the knowledge, right? So we're starting to getting civilized by the time where we're getting more knowledge and more information curated and putting together. And then, that's, the future. That's where we are right now. And then talk, how we exactly store the knowledge, right? So, back in 1883, we have this yellow pages where we're putting information together in a booklet. And still you can see those yellow pages being distributed, right? And then not until 1994, we have this Yahoo invented, and people were saying, okay, there's a better way of, just checking online or just typing that. And then by then, it's not too much of a search, but more about a categorized knowledge. So the knowledge has been put into those categories. And then moving forward, we have Google, right? So Google did one thing is that you can search whatever you want, right? So there is a very complicated system down there. All of the computer science stuff going there, they have the best engineer down there. So we have those crawlers, and we have those index, and then we index a huge amount of web pages. We have the PageRank algorithm, and then we have a huge library of stuff down there. So whenever you type a query, and then all those kind of gradient boosting, this feature engineering down there, deep models, they work together to serve you the list of knowledge that you wanted to have. Not until more recently, we have this, 3 years ago, now it's 3 years ago, we have the large language model. So it changes quite a bit. It still provides an interface where you can type a question, you can type what you wanted. And then what's underneath, it's changed, right? So it's a huge, we now know like it's a lot of transformers down there. It's a deep neural network down there. And then what this kind of large language model brings to us is that, from the perspective of machine learning, right? So we've been working on machine learning I've been working on machine learning for 15 years. And then the things that makes me personally excited about is one thing is kind of multitask learning, right? So you'll see a lot of these words in my research. But really before the large language model, a lot of times when we're trying to deal with one task, we have to build a machine learning model. We have to get the data, have the definition, and then we train the model, right? And then we generalize to whatever we wanted to generalize. But for large language model, we don't do that. Like we have the multitasking, right? And the second thing is in human knowledge integration. So we not just the data down there, we have to use a lot of human insights in that, using the human in the loop to reinforcement learning to calibrate the model. And then, what makes me more excited about is this kind of capability of reasoning over the multimodality, right? My research was doing, is over the past 10 years, is focusing on the three directions, happen to have these three directions. So MATLAB works on a lot of things about this function, right? Y equals fx. We build regression models. We build classification models. X can be, traffic trajectory, can be, what's going on in different lakes in the United States, can be a lot of different things down there, and why something we wanted to predict. Okay, so my research can be categorized on how we integrate different type of knowledge down there, and to build this kind of little FX right down there. We're trying to integrate different type of knowledge during the learning process, different type of data and data from different domains, and we try to put them together. And then putting them together is a very technical thing to do. And then sometimes if we deal with the real world data, by real world data, we mean, the data sitting down there, if you go to the hospital, pull the electronic medical records, you'll find out the data is a little bit different from the ImageNet or some kind of well-structured data that we've been dealing with. All right, a lot of times the data has been sitting outside in different places. They cannot be shared. And if you want to build a machine learning model over 10 hospitals, that they cannot share the data with you. So we have to have some kind of mechanisms to putting them together, putting the insights together, not putting the data together. And also a lot of times integration itself requires this kind of robustness, requires interpretability. So all of this gets to me, my research. And then my research is getting all those techniques, but more is AI plus X is like trying to anchor those techniques into different applications. So over my career of 10 years of professorship, I've been working on different type of applications over time as a computer science people. Back then we're pretty popular, right? So like back then we don't have large language model people rely on computer science people to code for them, to build machine learning models for them. But now the era is gone, we know that. But still, today I would like to share about one of the specific thing, which is my main research nowadays. It's about dementia. So through this use case, we'll see how this AI and X will be combined together. Different kind of challenges they can be putting together. I don't know how many of you actually watched this movie before. Actually, I watched the trailer right before I come into this room. This talking about a professor getting a dementia, and then this movie wins, I think, one of the Oscar award, and talking about the process, the dying process. A movie talking about a dying process of a professor, which is one disease that is behind this is called Alzheimer's. So what is Alzheimer's? Alzheimer's is one type of dementia that impacts a lot of people, right? So, and then it has a lot of symptoms, memory loss, and capability to reason, and in the end, you can't see things. So you can't basically navigate the room by yourself. In that movie, that lady cannot even commit suicide, even if they wanted to, because they forget what to do along the way. So it's pretty scary. And no one knows how to stop and slow down, prevent the disease. There's a huge amount of efforts. And I each have a one division called the National Institute of Aging, as pull billions of dollars just to do a lot of things about it. And it's just not so successful at the moment. So if you're looking at this neuron, right? So you see those plaques down there. So those are plaques that is blocking the nutrient pathway of this neuron. So this neuron is being attacked and it's dying, okay? And then that's not the worst part of that. It's dying. The next thing, right after this picture is that the dying neuron will be a part of the plaques down there and trying to block the nutrient pathway of other neurons. So it's you can think about it as like catastrophic feeling like one after another, right? So this is what we call a neurodegenerative disease. Okay, and then Alzheimer's as the sixth leading cause of death in the United States, and then it's pretty scary. And if you look at this neurodegenerative process, right? So this is the same person that is writing his own name over the years, and then you can see that by the time that the patient is about to die, it's not even be able to finish his own name. So this is a very scary stuff, right? So if you look at that, you're basically changing, you're fading away. You can see this person is fading away. And then the worst part of that is, by 2050, we're going to have more than 100 million patients over the world being impacted, right? So there are a lot of key barriers in Alzheimer's research. I'll just put it here. First thing is that apparently the Alzheimer's disease is not just one disease. It's not like a skin cancer. It's not like other kind of disease. It's not one disease. It's a very complicated pathology of multiple things going on together. So we need to have this kind of multimodality data to profile them, to do a subtyping of them. And then it doesn't actually have a reliable biomarker, by the way. It's not reliable, but accessible and reliable. The thing is that if we want to get diagnosis, clinically diagnosis, I have to physically walk into the hospital and then take a brain imaging or take what we call CSF, basically a lumbar puncture down there, getting the fluid from the spine. And then we're trying to get the CSF markers from there. As you can see, you cannot do that with a lot of people. It's very, very painful. It's very, very costly. Not too many people wanted to do that as well. So that's one of the things that if we don't do that, typically when it's getting very bad, it's late stage diagnosis. We miss the prime time for diagnosis, for recruiting patients, for clinical trials. We miss a lot of good time because we don't have the biomarkers. And then also the drug failure is one thing, right? So 99% of drug actually failed. Huge amount of money again, it's been failed, right? So how can we use AI to help on this directions is basically my research area. And talking about Alzheimer's, so Alzheimer's have this kind of progressive stages. So one of the stage what we have is, the very early on is before the Alzheimer's, it's kind of MCI, it's kind of mild cognitive impairment. And after that, the brain, different parts of the brain is going to shrinking, right? And then you will see that different symptoms actually appearing over time. And if you take a look at a healthy brain, which is on the left, and then take about Alzheimer's brain, which is on the right, so you can clearly see a very big distinction between them, right? And then that's actually good. The good thing in the sense that this is something which can be captured by medical imaging, right? Imaging, right? Imaging is talking about imaging. Imaging is one of the things that is a very exciting benefit from computer vision advances of AI, right? So we have the deep neural network. Nowadays, we can do a huge amount of stuff with imaging, right? So including the medical imaging itself, and we can track people real time. This is a picture like 5 to 10 years, 5 years ago, right? So when we only have the AlexNet and the VGG network, we can do something very fancy like tracking people around. Back in my time, one of the movies that was interesting is Resident Evil, right? So you see that AI is tracking people in real time. By then, it's pretty hard. You create a support vector machine, you have to, create a lot of features, and then trying to make the classification, figure out the bounding box. It's actually pretty hard, but nowadays it's so easy, right? So what behind it is the involvement of AI and machine learning, where we have a lot of powerful models, right? Starting from the simple MLP, but all the way to the convolutional neural network and attention models, the transformers, what we have right now. And what's behind that is a huge amount of training data. So you need a huge amount of training data to train this model, right? So for example, like the ImageNet, right? So we have 14 million images, right? So we can use that to train computer vision models, which is cool, right? And then here, I want to stop for just a moment to cite Rich Sutton's Peter lesson, right, to 2019. We're saying that, read this way, seeking an improvement that makes a difference in short term, researchers seek to leverage their human knowledge, right? But only thing that matters in the long run is leveraging of computation. Can you feel the vibe here? You know, like computation, ultimately the computation. It's true in the sense that, you know, it's contrasting the human knowledge and the computation, right? It's true that we use the scaling law for neural language models. So we have the language models we have right nowadays. We know that for more computing power, through a huge data size and more parameters, we're going to get better performance. So people now are no longer talking about thousands of variables. Right? Think about that. Back when we're talking about big data, we're talking about thousands of variables. And then, you know, like millions of samples, they call it big data. But now you see, we're talking about billions of parameters, right? So like terabytes of training data down there. It's just crazy, right? So, and then this scaling law, does it work for the AI plus X problems, right? So the problem that I mentioned about the dementia and stuff like that. Otherwise, we'll just throw in more money to create the data and then maybe create the data and then throw more money to get the computing. We've solved all the problems in the world, right? So we can just solve the dementia, solve the cancer. Can we really do that? So my research involves building what we call a disease progression model, right? So that's and I started doing this when I was a PhD students, where we're looking at the medical imaging, look at the blood and genetics, so trying to predict even all this information for one patient, what will be some of the cognitive status in the future, let's say 1 year or 2 years later. How can we do that, right? So we're starting with the medical imaging. And then the data that we're using is one data set where we could add so Alzheimer's disease neuroimaging initiatives, right? So talk about this data set. This data set takes 5 years to collect. It's an NIH project, and then $6 million thrown into that. Now that's a long time ago. Now you can think about now the inflation like this. We're easily talking about 100 million or so. And then we have 900, 800, a little less than 900 samples from machine learning scientists. Can we talk about scaling law here? Perhaps not, right? So we can't scale with 900 samples. Even have 900 samples, we can scale them. You know, the large language model and stuff like that simply doesn't actually work that way in the many of the AI plus X, right? Over the time, you know, when I was working on this early diagnosis and discover biomarker, build this machine learning in this type of data. And then there's something we're trying to do just to mitigate the issues we just mentioned about, you know, 800 samples. What can you do? Of course, over time, the NIH put a lot more money just to get more data, right? So let's say, for example, the ADNI data, nowadays, they have 4 NIH projects like that big, and then that created around 2,000 samples. Okay, so the 2,000 is all you get. And then how can we learn very complicated machine learning model that way, right? So there are a couple of things we do, you know, along the way. One of them is, of course, incorporating domain knowledge, right? So we know that machine learning is giving the data. Machine learning basically turn that into an optimization problem. And we're basically navigating into what we call a search space and trying to find a solution of down there. And then something we can do is we can always translate some of the human knowledge to guide the machine learning process so that we can reduce the space for machine learning to search. Of course, if the prior is good, it's great, right? And then the next thing is that we can fuse multiple type of data, right? So if we have like multiple views of the same subject, we have multiple data sources, we can put them together, okay? We can put them together, and then we can use them, you know, use the consistent information among all different views. And of course, sometimes we can do multimodality, right? So we have information from imaging, we have information from genetics, different type of imaging. We can find something with a common subspace down there. We can create a subspace, we can mapping all those data points down there so that, you know, in a subspace, which is basically a fusion of different information types down there. And then we use that to do this subtyping, disease progression. It hopefully can help us a bit more. And then, you know, sometimes we have different targets, just echoing what I mentioned in the very beginning. Back then, machine learning, each prediction will you will have each model, right? So you have individual model. So if I have 10 different scores down there, I need to predict those 10 scores may be related somehow. So we can correlate that learning process. So we can learn those 10 models all together by building some kind of relationship so they can benefit from each other, right? So my learning can benefit your learning and vice versa. And of course, and there's another thing is that the real world data is usually very, very noisy. Okay, and then so noisy that a lot of times, maybe no, we're not talking about majority, maybe 30% of the data, the labels are wrong. And then when this type of data enter a very complicated machine learning model, let's say a deep model down there, it's going to propagate all the way through your network. And then your network, powerful though, it's going to capture all those errors in there, right? So make your generalization a lot worse than it should be. So a lot of times we have to, like basically work on the learning process, how to detect early on the issues down there and filter them out, right? Of course, domain adaptation. So that's what everybody's doing, building a huge foundation model, and then trying to fine-tune the foundation model into some of the downstream tasks so we can benefit from a lot of massive amount of data down there, even though the data is distributional different from what we are working on. Okay, so we're talking about all of this, right? So, and then we build some of the very good models for imaging, or some of the other markers, fancy markers, trying to predict the disease trajectory. But there's one thing having thought, like still bothering me back 2020, right? So it's like if you take a look at a few curves, right? So one curve here, you can think about this red curve, this blue curve, and then also this green curve. Those are pathology, like the evolvements, what's going on in the brain. And then this purple curve is really the memory, right? All of a sudden, I lose the memory over and over. I find myself something wrong with it. And then that's the purple curve. And then when the purple curve reaches to some stage where, like, I can imagine that if I walk into the physician and say, hey, I'm losing some of my memory, the physician, okay, that's fine, you're getting old. Like you don't get more coffee when you have it. But when things are getting really bad, right, you can see that my brain structure already pretty messed up. Okay. And then one-side information for those of you who are studying engineering and then hired and gone through higher education, our brain has a mechanism that trying to reroute some of the information if some of the structure is broken, meaning that it's even harder for the technique to detect us if we have Alzheimer's, right? So it's getting very, very late. The brain is totally messed up before we can find it. So at that stage, you see, it's pretty hard to do anything. And it's pretty hard for those medical researchers to to have you enrolled into some program. So, like we develop treatment or, do the drug trial. So can we develop some kind of detection approaches that is affordable and accessible? As one of my major research direction after my tenure back in a long time ago. So that's something I was thinking about. And then something inspires me. Oh, yes.
Can be a dumb question, but before you said that there is no way to stop or slow it down. So what is the advantage of detection?
Right. So that's a good question, right? So remember, there was one slide we mentioned about the issue. So why it doesn't work? It doesn't work because typically when like you see, biomedical research have a lot of things. One thing is to collect the data. We need, let's say, machine learning model to follow those patients for a long time before it's developing all those complicated symptoms all the way to what's there. We need to detect it early before we can collect the data, before we can actually do something about it, right? Find out the biomarker, building those kind of disease progression model, that 800 people can be 8,000 that can make a difference, right? And then also, if we have more people, we can experiment with interventions. We can try different drugs. Our drug trials can be even cheaper, so we can try more drugs, right? So something about AI is that we can still do a lot of things. Okay, yeah, sorry for this. This is one of my favorite novels, right? So Murder of the Orient Express. So it's by a famous author as Agatha Christie. And then this lady is died because of dementia, because of Alzheimer's disease. And then one of the things down there is at the very end stage of her life, her writing actually changed. right? So I highlighted it here, the vocabulary size getting smaller. The way that our brain put together information to create those kind of, what we say and what we write gets more simplified, right? So meaning something actually can be detected down there, right? So my research was more using language as a window into the cognitive health, right? So what I'm doing here is, because language is pretty cheap to collect, right? So like if I'm reading a paragraph, if I'm reading a news, some of the tones can actually change. If I'm, talking to somebody else, the conversation can actually reflect some of the information in my brain as well. It's very easy, right? So we're talking about something called a language marker, which means the information is extracted from the language, okay, that is related to the disease, right? So moving forward, I'm going to talk about two things. One is kind of early detection. How can we build these models? What are the challenges and the progress we've been doing to assess the cognitive health through the language? And the second part of that is how can we do some kind of intervention, right? So we have large language model, and large language model actually help us do something about it. All right, first part of the early detection. So this is a paper back in 2021. So it's one of the paper we're showing that if we have the data, right? So this data is collected from an experiment. Some people are trying to describe what's going on in the kitchen. So think about that. Every subject is provided with the picture, and this picture we're talking about. Okay, some kids is about to fall. This lady is washing dishes, is having overflow water. So you see all these descriptions, right? So you just ask different people to read about what's going on and collect it and transcribe it, and we have the data. If we further moving forward and collect the cognitive scores reflecting their cognitive health, and then we can build a machine learning model, right? So the model X, what is the X down there? The X down there is everything inside of that transcription. It could be some of the words usage, it could be some of the syntax complexity, it could be a lot of things down there. And then what is Y? Y here is that, if it's normal, if it's dementia. And then it's not hard to think about, right? The dementia subjects, they have a much different way of speaking than the cognitive normal subjects, making it a very easy machine learning task to do, right? So, back then we extract a lot of signal processing kind of features, and then we use the, BERT and some of the word categories, the RIWC, and we're trying to build a rich set of features, and we're trying to use a logistic regression, okay? And then just to make it happen, the reason that we're using logistic regression by then is because we don't have that many subjects, right? So we're still using linear model, but we're incorporating some of the large language model, not so large as compared to today, but BERT is still transformer based. And it's actually, yes.
This setting, how do you get the ground truth? These patients have the PET scan or the spinal tap or whatever?
They have clinical diagnosis. So there is one stream to do clinical diagnosis, neuropsychological tests. And then with different tests and the different risk factors, they have this kind of guideline from the health department. We're saying that who is clinically diagnosed as Alzheimer's, right? Yeah, Alzheimer's, the final diagnosis is down when the patient is dead, right? All right, so you have to look into the brain. Yeah, that's a good question. Yeah.
Just follow up on that. So does the image also be some the established biomarker for the clinical diagnosis?
You mean the medical imaging?
Yeah, because the imaging is showing something different.
Yes, that's right. Yeah, there are established imaging biomarkers down there.
I see.
Yeah. All right, and then some of the other things we're trying before is that we try this multimodal markers, right? So we combine what's inside the language with acoustic information, right? So the thing is that the acoustic information contains something, the tone, let's say, for example, if I'm trying to remember something, right? So my tone can be changed as if I remember something very well. So if we combine something, there's two data modalities, we can show increased performance as compared to using just one modality. But there's nothing that is easy to do it because there are a lot of challenges associated with this type of what we call digital biomarkers. Right? So the digital biomarkers, there's one thing that is, if you take a look at this, right? So what is this? This is basically each point down there is someone who's talking about something. And then you have this transcript and you have this implicit information. And then you have extracted this kind of feature vector down there for that person, for that conversation. And then for each person, you can have multiple conversations down there over time. This is like multiple conversation over weeks. Each point is like 1 week, say, for example, and then, different weeks. And then each of the color is coming from one subject, right? So you can see that all of them, if you project them into a lower dimensional space, they're clustered. What does it mean? If you're trying to learn a machine learning model, saying that, hey, those are my training data, and then I want to differentiate this disease and the non-diseased people, and then how would your machine learning algorithm react in this way? I will say machine learning algorithm is very, very simple. Gonna basically find out easy, low-hanging fruits on the classification boundaries and follow through some of the patients, right? So it's not gonna very easily find out is disease or not disease. We're saying, okay, I have this is disease, it's not disease. I'll just build a decision boundary down there. So machine learning algorithm, this heuristics, it's not gonna help us find disease or non-disease, given the data is so much like clustered in this way. And I hope I can convince you that. So that's gonna give us one challenge, right? So this challenge is something what we call a generalization issues down there, right? So if we ever have a new person down there, let's say a new person down here, and then that decision surface is not going to be very effective for any of the new patients down there. So how can we do that? So we basically create some kind of harmonization approaches, trying to remove the information in the data that can differentiate between subjects, right? So some of the machine learning approaches we can do to do that, to remove some of the subspace that is differentiating different subjects. And then we can also extend that into temporal, right? So now think about if we have multiple weeks, each of the week have one conversation, we have those kind of trajectories of features. We can also do something about it, right? So we can extract a temporal, like dynamic features on top of that. And then we can also need to do this kind of temporal kind of harmonization on top of that. So so there's one specific thing I wanted to show you after all of this is like language markers. Still, they're from language. So it's, each day we're having a different mood, and the language can be highly varied, right? So even for me, for one of the subjects, for over different time, you're going to be highly varied. So even though it's accessible, if we're using that, because of high variation, it's not going to give us high accuracy, right? So how can we increase the accuracy of those biomarkers? So that's one of the questions, right? And then happen to have, for some of the subjects, we do have the medical imaging down there. And then is there something we can do about it to calibrate this too, to make it, like this cross-modality kind of alignment can help us with that. This is not a easy thing because we can't use medical imaging after this language marker is deployed, right? So we can't say, okay, before you use my software, go to the hospital and get the imaging. It loses the value of everything we're doing, right? And then so this additional modality only appears when it's in the training phase. Okay, meaning that during the testing, it's going to go. How can we do that? So the question is, can we use this accurate but sparse imaging markers to improve language model during the training, only during the training? So how can we do that? So our solution, we try something we'll get a cross-model data augmentation. So basically what we're trying to do is here. We're trying to build, let's say, a language. You can think about this language as a space, right? So language features is like one subspace where you can have them. Can all have all your subjects in that subspace. And then in the imaging, you have another subspace. Okay, that subspace is for imaging data points down there. And then we're creating some kind of mapping, trying to connect this to subspace, through this very, very limited subjects. that has two modalities. Okay, once we bridge this two modalities, the next thing what we can do is we can use, we can go across different modalities. Let's say, for example, if we have a new patient, we just have collected their language features. Okay, the language features we can use that mapping we built through limited amount of people, and then we can go across to the other side and go to the other subspace that is built by imaging. Of course, for this subject, we don't actually have any imaging at all. But what we can do is that at that other subspace, we can use nearest neighbor, trying to look around, trying to see, are there any patients, during the training that have imaging that is close to what I'm saying, okay? And then this is gonna give us some of the estimation of, if this patient is gonna have imaging, what would the values gonna look like? And then through this very simple, like contrastive multimodality learning, and we can actually increase 10% because the features or the models that we're creating are now biased by the imaging during the training and only during the training. Okay. All right, due to this time, I think I'm gonna speak one of the work down there. We even built some of the chatbots down there, trying to diagnose, trying to make the conversation more efficient. So basically, this is a long time ago, like 5 years back. When we built this kind of chatbot, so the chatbot can talk to the patient in a way that is not taking hours, but just to taking a few rounds, trying to ask very specific question so that it can actually increase all these classifiers down there, right? So how can I ask something so you respond? And then fit it into the language-based classifier, let's maximize that confidence. So there's something what we do, right? So this is basically cut down a lot of cost of collecting those features, those language features down there. So I'm gonna quickly skip that. But there's another thing I want to talk about, using the time. The thing is got a chatbot for dementia intervention, right? So we talk about early detection. We talk about how to build language markers, those features and those models, trying to differentiate, okay, early dementia or early MCI, and then the normal. But how can, is there any something we can do about it, right? So in the United States, for example, in the global population, there are 4% of dementia cases are related to social isolation, right? So like seniors living by themselves. Sometimes they live in the senior home and then there's nobody to talk about, right? And then this is very, very common, right? So down there, and then those populations is especially vulnerable for dementia. So we have another, our collaborator actually had a clinical trial showing that a frequent stimulation of the conversation, stimulating conversations can actually reduce the cognitive decline in those populations. Right, so there's another, I think it's a paper 2 years back. Based on this, basically what we're trying to do is we're having this kind of NGO, so we build a nonprofit down there, and then we're trying to do a couple of things, right? So we're trying to recruit those socially isolated people here, and trying to say, hey, there's something we can do to help. And then on the other hand, we basically train a lot of volunteers down there in the United States, and trying to them to do the weekly phone calls to the seniors, right? So so far we have a bit less than 100 participants down there where we have weekly phone calls to them. So that providing some kind of clinically proven protocols to stimulating their cognition. But this process, like over the years of efforts, we can only scale this much, right? Otherwise, we have to bring more people, to more volunteers here to make the phone call. And we have to train them one by one, what to do. And then this doesn't actually scale well, right? So many adults cannot get engagement during this kind of resources, and then they don't actually, we can't train them much. So how can we do this, right? So is there anything we can do about it? So we're thinking about, because we're doing AI, thinking about it, AI chatbot can maybe helpful here, right? So naturally, we're building this kind of AI chatbot for dementia, right? So it's an intervention. So this can be done by human and probably can be done by AI, and maybe not effective, but there's something we can do about it. So we actually built like a chatbot, right? So powered by this kind of clinical proven protocol down there, and then we can use that to offer service through the phone call to those socially isolated seniors down there. Right down there is, of course, a lot of prompts engineering down there, right? So we have to specify how this kind of chatbot adhere to the clinical protocols that is used by human. And of course, through this prompt, another thing we have to do is we have to so we have to evaluate, we have to improve the prompt. We have to know how the prompt is going, right? Normally, if we design the prompt, we incorporate that into the chatbot, and then we have to wait till, let's say, use it for a while, and then see how good they are. That's going to be very, very, very challenging to improve the prompt, right? So, one of the papers, what we do is we develop this kind of digital twin kind of thing as other language models. Basically, we're asking language models to simulate this patients. And then we have a master language model that is talking to that simulated patients so that we can evaluate instantly how to change the prompt. How can we maximize the prompt with respect to the performance of the chatbot? Of course, we can do something more. We can actually develop a very sophisticated conversation strategy. We can optimize through the same techniques. Okay, and then in the end, we're thinking about this multi-model foundation model. I think still the future of the healthcare. We're trying to put together a lot of different data sources and then trying to link them together. And then, if possible, we learn machine learning models through this kind of discrete data. That's something I think is going to help in the near future, right? So I'm gonna skip this part of that. Right. So I hope that through all this experiments and all this kind of results, I can convince you that this AI plus X is not so easy as compared to many of the machine learning applications, because the data, the challenge from the data, the challenge from all this kind of real world data is kind of require a lot of innovation, still require a lot of innovation from the machine learning side of that. And then in the future, I still think about this kind of collaboration between this AI and X. I still remember the first NSF grant I get back in, I think it's almost 10 years back, right? So that's proposing this kind of things like interactive learning, right? So the learning process, we put the human inside of that, okay? Human in the loop, basically, right? So nowadays we're still talking about that. So there is one prototype that we're building for the drug discovery, which is another line of work we're having, as we're trying to find these molecules through this machine learning search process, and then we're trying to involve human in the loop, right? So there's this is something I have in mind a couple of years back, we have this knowledge. And then we use large language model, foundation model to integrate this different type of knowledge. And the human experts is going to interact with that. And then all of this is going to drive, like in a search in the subspace. The subspace can be a molecule, right? So it can be drugs, right? The drugs can actually, we have a machine learning algorithm that is driven by the human and find new drugs for things that we want it to be. And then, we have another paper recently, just submitted. And then it's talking about how can we achieve this, and then what is the limitation, technical limitation of this. We're going to have an archive version of this pretty soon. It's like diffusion, using the language, drive the diffusion to generate molecules. And then all of that, I would like to thank all my lab members, been there before. And then thank you so much. Yeah.
For the fantastic talk, I really learned a lot. You just come in. Yeah.
On slide 82, you had a maximization of the prompt. Are you maximizing over tokens, which might give you the best loss, but maybe, or whatever you're maximizing, but do you actually end up with a prompt that is human interpretable?
Yeah, that's right. So they're talking about this one, right? I just want to make sure.
Right here.
Oh, yeah. So, yeah, that's right. So this basically thinks that given one prompt, right? One of the things what we can do is we can use a large language model to have a chatbot. And then our digital twins over our training data is going to interact with that. And then we're going to extract some of the metrics of how they talk to each other, right? So we have the evaluation over all the digital twins we built. And then I think the interesting part you mentioned about is this, right? So how do we actually do the prompt? Are we gonna basically do this optimization based like token wise search? So well, actually we did not, right? So we come up with new prompts down there, like human, like create a bunch of 100 prompts down there so we can compare. So it's still a prompt. There is a constraint here belongs to human created prompt down there. Right, but I agree with you there. In the future, we can do automatic prompt learning. We can even throw into a large language model saying, hey, revise this, right? So yeah, something we can do about it. Yeah. Yeah. Thanks for the question. No.
Guys are all typical. They're designed right.
Yeah, that's right. So we know that what is the instruction down there for the large language model.
There are some questions online asking for the email address for you and also.
Oh, okay. So that's oh, sorry, that I can share that to the audience if needed.
Yeah, we do have the recording
Right.
for that will be put online. So yeah, hopefully that slide will be good there. Yeah, so yeah, I also ask people like ask a question on the room if they have any.
Yeah. Or feel free to send me any emails. So yeah.
Yeah, also some question about the last part for the drug discovery.
Right.
You also mentioned the LLM is integrated in this process, right?
You mean in this process, right?
Yeah, or maybe I misunderstood that. I also wonder like, since for the drug, I have the graph, there's the structure.
Right.
How that is optimized, you mean something like diffusion? Yeah, maybe. Could you-
Right. I can use this as one example.
Yeah.
And there are so many different ways to deal with the drugs. As you can see, the drugs are chemical molecules, molecules, right? So small.
Yeah.
When we're talking about drugs, we're talking about small molecules. And then when the small molecules can actually be converted into a string, first of all, right? So if we have a drug structure like this can actually be represented with multiple strings, right? So to represent the chemical structure. And then, of course, the simplest thing for a large language model to handle that is just to put the string down there, right? So the large language model can understand it.
I see, without any fine tuning or.
But with fine tuning, we're talking about how the large language model can feel the machine learning can actually feel the molecules, right? So one way is use the string and then use the large language model or any of the attention models, get the tokens about that. That's something doable, right? And then you can also generate those tokens as well, right? So that's something you can do. And then the other thing is that not all those sequences of strings are valid molecules, right? Sometimes a large language model using this next word probability, next token probability, may construct something that is invalid, right? So as you can see, something you can do is to fine tune them, right? So in the hope that through the fine tune process, the training can actually tell the large language model what are valid molecules, what are invalid ones. But that's not approach that we're doing, right? So what we're doing here is more you think about the latent space. We're using what we call latent space. So we're basically having an encoder and decoder train. So that encoder is going to encode this molecule into a point in your subspace. And then we're going to use diffusion to get into other places in that space. And then that point through the decoder can decode into a valid a molecule, right?
You're actually train some diffusion model to convert object to the molecular structure.
So that part also a lot of people are doing that. Right. So what we're trying to do here is text-driven kind of diffusion process.
Oh yeah.
So we use text to guide the learning, guide the discovery of new molecules down there.
I see. But is this something we call your guidance is only from the text, or you want your generated structures once they satisfy, for example, some biological or chemistry like requirements, right? Is that also something that we need to consider for the discovery?
Oh, that's very, very, very good question. So in this demonstration, in this paper, we're basically talking about how complicated structures needs to be decomposed into different parts to guide the diffusion process. And you are right, in the actual drug discovery, we want some of the molecule to, let's say, if we discover a molecule cannot even be dissolved into the water, then there's something bad. We want to add this kind of functional like properties down
Yeah.
there, rather than, just a structure description down
Yeah.
there. That requires much more fine treatment, which is something we're doing right now.
I
At the
see.
moment that you're talking about, like,
I see. Yeah, that sounds quite interesting.
yeah, we can talk about more details down
Yeah,
there.
exactly.
It's something we're experimenting with, like different subspace. You're trying to think about it, like if I have 10 different required properties down there, I'm
Yeah.
searching the molecules in 10, you can think pretty much independent kind of subspace, right?
Mhm.
So, and then you want to find, if, you want to find some valid ones in different subspaces, which makes it much, much more complicated. Yeah.
Could be.
Yeah, I had a question regarding the digital twin. So. Here, yeah.
Yeah.
So, in this case, the digital twin is created. By only using the language data.
Yes. We just fine tune a language model using the previous collected
Would it be
conversation.
helpful in terms of multimodal data, that we collect also, for example, the video data or camera data in terms of behavior of the patient,
Right.
to see what the patient has decided in particular circumstances,
Right.
and collect those data, and then produce a digital twin which also includes the behavioral data. And would that be helpful in this case?
All right, thank you. Yeah, so that's something actually we can actually do it, right? So the hard part of this is really about the I think the data part of that, right? So do you have the data or not? If you have the data, you fine tune, let's say, a generative model to generate the avatar, we can do that. And also fortunately we have the data, collected during the conversation. So yeah, so definitely it's something doable and helpful. Thanks.
Awesome.
Because
Yeah.
going back to my earlier question about how we got the ground truth that classification biology.
Right.
You said the answer was by using the clinical system. But I mean, so we already have a classifier, it's the one where the doctors use based on the clinical system, so I didn't quite catch what is the, don't we want to be able to design methods that can catch it before they notice it clinically or something, right? So
Right.
Early detection or something.
Right, so that's why it's one of the first work we're doing, right? So what's inside the language? But think about that, as we're communicating, there's no physician involved. There's no neuropsychological things involved. There's no interview saying, hey, do you know which floor it is? Do you still remember what is last meal you had yesterday? You don't have this question like this, pretty natural, right? So conversation down there. And then someone sitting there, some AI agent sitting there, just trying to document those features, right? So this, like pop-up risk if needed, right? Yeah,
Something like the proactive.
it can be,
Yeah.
right? Yeah,
Yeah. Point doctors.
Yeah.
yeah. Getting to doctor is really hard, huh? Yeah,
Especially.
yeah. That's right. That's right.
So size of the unique, the number of the unique data and share the early detection models. Where there's the number of species.
Sorry, can you say
The
that question again?
the number of the unique image.
The number of imaging,
Use your number. of
Right.
Then we should get a model.
right?
So the data size of the image is where there's the
Yes, that's right.
smaller than the language model, language data.
No, I can't say that. So the language, depending on what kind of language, you see the challenging, any of the clinical data, we have millions of brain scans down there, right? And then when I really want to build a classifier, I need to have, let's say, a positive class and negative class. Positive class is kind of case and, negative class is control. I need to build this case and control. So meaning that not only I have this imaging, I need to know what is a subject, what is a person. And then if the person 65 plus with some kind of prior condition that satisfy a case, and then we have to know that the matching controls will have similar condition of that. So building a machine learning model collecting the data is much more than the imaging itself, right? So the imaging, we have a lot of imaging from all different people, right? So we have the Michigan medicine, we have this imaging, but in order to study the dementia, you have to have very specific population. To answer your question, we have a huge amount of imaging, but we don't have imaging associated with the clinical scores of the patient. So, making the sample size much smaller. And sometimes if we're trying to learn this trajectory, we have to make sure the same subject is there for multiple years, not dying within 5 years and, willing to step in to the clinic to take the scan, which a lot of people feel uncomfortable, right? So, moving is not good. And not to talk about, if it happens in COVID, you're not even going out of the house, right? So that's what makes the medical imaging part hard, aligning those different modalities. And then for the conversation, it's the same thing, like that conversation data is coming from, I'm using right now, is coming from a 5-year R01, which planning to have 200 subjects being collected, only 200, right? So 200, only 200. And then this 200, every week we have to have people to follow up in that, right, for 1.5 years, and to build this cohort. And some of them, we need to also align them with the clinical variables, right? So there are neuropsychological tests or brain imaging stuff. So making the sample size cannot be too small. And then that's an R01, in case you don't, like R01 is like typical the maximum we can do within, with a single PI kind of, with, a single project, right? Yeah, so to answer your question, we have less people in the conversation side, right? And then another thing to consider, I think it may be relevant to what you're asking, is that the small sample size in the language is not a huge concern in the sense that the feature size can be much smaller than the imaging, right? So the imaging, you have a huge like input, and then you have to extract features in the imaging, which make it, even building the same model, you need to have more samples to do that, right? So, yes, sorry, I extended it a little bit, right? So the sample size is not comparable. My point was, yeah. Yeah.
So at some point after the clinical protocols, then you go to virtual conversation. Then you analyze those. My question is there a threshold from which you go from real to virtual conversations in terms of so I'm thinking initially you collect the data from the users, you do virtual conversations with the patients and so on. But at some point you have a user digital twin. Right? So can you at some point start interacting with the user digital twin and retrieve data from that? Because at some point the user digital twin, if it is good enough, the user digital twin would respond as the patient. You see what I mean? So at some point to talk with the patient's digital twin instead of the real patient. Can at some point that be achieved? If the user digital twin is so advanced and so powerful that it really, mimics the.
There are two answers for that. One is Michigan answer for that. Yes, I believe sometimes it is going to be happen. As a machine learning scientist, I don't believe so, right? So to build something real simulating people, you need to infinite amount of data to do that. But we don't have, right? Like in this case, I may have like a couple years of conversation with the patient. That's all I have, right? I don't actually know. I don't know the complicated mechanism down there. What is driving the human speaking and stuff like that, right? So like, yeah. So I think clinically, if we have more data, we can actually do that. But for machine learning, if you really want to skip the real patients, talking to simulated patients, we have a long time to go, right? Yeah. All right. Thanks.
Okay, thank you.
Yeah. Thank you.
I think there are some people asking for your email. I just have it there.
Oh, yeah,
And
yeah.
everything.
Thank you so much. Yeah, I didn't,
Yeah.
you know, minimize everything. I don't actually see anything down there.
Why is not showing?
Yeah, you know, that's, I don't know, like that's.